a joint work between ARM, among ARM, Pragmatic, and Manchester University. This is the outline of the talk. So I'll do very brief history of processors on flexible substrate, or as we call it, flex processors. And then I will describe the driving market for flexible processors, and then introduce the title of the talk, obviously bespoke processors, what they are, and then motivate for flexible bespoke processor developments. And then I will introduce the development tool we developed from application to fabrication, a bespoke machine learning processor for flexible substrates. And I will also talk about business and research opportunities open to everyone, and then conclude the talk. So I like to start with this roadmap created by the Organic Electronics Association 2 years ago. What is important, what is significant on the roadmap is the long-term predictions. If you look at the last column, long-term 2024 plus, I just want to highlight these two bits. So the first row is the electronic individual discrete components, what is predicted in the long term. And in the second row is the integrated smart systems, what's happening in that domain. So integrated smart system is a system where the system contains multiple components like sensors and logic and memory and comms and display and several different IOs to put them together, and it builds, creates a disruptive products in the flexible electronics domain. So what is significant here is the printed, in the first row is the printed complex logic, and in the integrated smart system is the ambient intelligence. So this refers to processing or local compute on the flexible device or in flexible integrated smart system. So obviously it says printed, but logic doesn't have to be printed. As I talk in this presentation, that the methodology we use is not printed but more lithography. So moving on to the very brief history of flexible flex processors. So maybe most of you are aware of the work, but this started in 2012. The world's first 8-bit CPU built on a flexible substrate by IMEC, who is a research institute in Belgium. Although it was not a commercial CPU, it was a subset of an 8-bit CPU. It was a great milestone, towards developing flexible processors. So their first attempt was only in 2012, based on only organic p-type. But 2 years later, they did the hybrid CMOS, meaning that the p-type transistor was organic and the n-type was metal oxide. So the number of transistors is about the same, but this was a very good step towards building flexible processors. So the second project I'd like to talk about is something we are following in collaboration with Pragmatic at ARM. It's called PlasticArm research project. So it's actually taking a product quality Cortex M0, 32-bit Cortex M0 CPU, and build a very basic system on chip, meaning that it has not just CPU but RAM, ROM, and basic debug and serial peripheral interface, etc. and obviously this is an ongoing project, so we started this in 2000, late 2014, 15. Now it's still ongoing project. So after this brief history, I'd like to talk about at least contrast the processors in the silicon world today and processors in the flexible. So I don't want to confuse you, so I'm not doing this because the flexible processor is a competitor. It is not, so it just tells you, what are their technological properties and what are their target use cases. So if you look at the silicon processors, the transistor type is MOSFET, the flexible processor is a thin film, and substrate material is silicon, and obviously, and flexible in the flexible processor world is flexible substrate like mainly plastic, but it can be on paper as well. So logic type is CMOS in the silicon world, and it gives a nice low power property. Flexible in the flexible world, it's NMOS, PMOS, hybrid CMOS, but there is no true CMOS yet. But it's on the roadmap. It's going to come sooner or later. And the fab cost. So that's also another differentiating factor. So if I can use the pointer here, yeah. So the fab cost is could be 100 million or more. For the state-of-the-art feature sizes, it can be even billions. On the other side is only a few million dollars. So wafer production times also another differentiation here. It takes about 1 to 2 months. You tape out something in the silicon world, and it takes months. On the other side, it can be days. Currently, it's weeks, but it can be shortened into days. Addressable device market, which means that what these processors are targeting in terms of market. So silicon normally goes to server, HPC, PC, mobile, embedded, but the flex processor are not trying to build a flexible server processor you put in a data center. It's more mainly IoT, smart objects on everyday products. So another interesting comparison point is the lifetime of these products, where they contain the processors. So in silicon, you buy some mobile phone or some device, you expect that it will work for many years, mainly like 3+ years. But for flexible processor, depending on the application, if it is used in a detergent package, smart package, its lifetime is days. After it's been used, it's going to be disposed. So the spectrum is very high, from days to weeks, or even in rare cases is years. The other thing is the IC volume. So the integrated circuit volume in the silicon is in the billions domain, but we expect that flexible process, because of these short lifetime products, FMCG, as we call it, fast-moving consumer goods, it can be more than 1 trillion a year. So after this gives you the big picture, so let's discuss what are the driving markets for the flexible processors. So fast-moving consumer goods, as I explained, these are the products that we use. They are sold very quickly in low volume, low cost. So, for example, food packaging, smart deodorant, and smart logistics. I'm going over this very quickly. So interactive magazines. So these are their product lifetime in this domain it can be days or weeks, or sometimes just months. So the other interesting market, driving market, is mass market healthcare. The keynote speaker this morning talked about the health monitor with the e-skin, but there are other emerging applications like smart wound dressing. It has everything. It has sensor. It has some I/O indicator, and it will have some local processing compute. smart patch as well. People are building smart patches with onboard processing in it, and most recently the RFID tags for tracing the medical samples, as well as the smart blister applications. When you take a pill, it gives you a signal saying that you're adhering the prescription prescribed by the doctor. So these are again their lifetime of these products will be relatively quick. You use and dispose. So let's look at some prediction for the processor in the flexible electronics domain. So in the short term, we predicted hybrid integration is the way to build the smart systems in smart objects, meaning that you use silicon dies and integrate with the flexible or printed sensors. Some of the talks today was about integrating with silicon. So the cost is slightly higher, $1 or a little bit more, using microcontrollers. So we predict that this is just a transitionary period. So there will be something called progressive period, where we will see flexible bespoke processors as well as flexible general purpose processors. Obviously, the key market for the bespoke processing is the fast-moving consumer goods and mass market healthcare. So flexible general purpose will have some use cases where programmability of the processor is preferred. So let's look at the bespoke processors very quickly. Introduction. So I put it there. A typical microcontroller, silicon-based microcontroller today, it has everything in it. You don't have to, even if you don't have to use it. So this is called a Turing tax. I don't know if you heard this. I like this term a lot. It's coined by Professor Paul Kelly from Imperial College. So it means that this is the price you pay for universality in computing. You buy something, it's so programmable, but you also pay tax in performance, cost, and energy. So this is the difference between a special purpose device and the general purpose device. So all these things for your application, you may not need it with the red cross there. So if you get rid of this, and then the remaining things stay in the chip, is just doing your job, you're good to go. So this gives you a low gate count, good energy consumption, and low cost, and probably better sustainability, because when you dispose it, you dispose less material. So bespoke processor. So what is a bespoke processor? So it's a processor customized for one application or a class of applications. So it has two. It's a family with it can be either subtractive or additive. So subtractive means that you start with a product quality processor, and then you take your application or set of applications, and then you profile characterize, and you say, I don't use 40% of the gates. I'm gonna get rid of them, although keeping the original product quality CPU, but very smartly peel off unused stuff. What is at the end is something that runs that application, but you can't reprogram it once you implement it, tape out, and get that chip. But you start with a general purpose programmable processor. On the additive side, you take the application, you say, I don't want to use any general purpose processor, I'm going to build up from scratch. Here's the application, and build up, add the stuff application needs. And so this is what we call additive. This is also not programmable, but if you can build the additive processor, a bespoke processor for a specific domain, meaning that it will execute or it will run applications from that domain, but outside of the domain you can't program again. So it has pros and cons, but the common properties is that it gives you lower power and lower cost, and it's relatively, I use the term relatively, simpler to design and verify compared to bigger, more general purpose processor. So let's look at their outlook. So what is the, so this is nice, the y-axis shows the programmability, meaning that how programmable is the processor. Product lifetime it shows that this processor goes into a product, what's the lifetime of that product? So if you look at the bespoke processor, we predicted the product that will contain the bespoke processor will have days to months, and will be super high volume, like FM, fast-moving consumer goods or mass market. And because of the the high volumes in these markets, as well as the low cost in flexible electronics fabrication, will justify bespoke design. So in the silicon world, this contradicts with the silicon world, because people do bespoke design, it costs a lot. But here, it may not cost a lot if we target the right market. This is the differentiating thing. And another thing is that because they are moving so fast, the product lifetime is so short, you don't need to program anymore. Why would you use a general purpose programmable processor? Just use something bespoke. Maybe 2 days later, you finish your milk, there is a processor in the packaging, you throw it away. So there's no need to program that. But having said that, there will be definitely a use case for general purpose processor on flexible substrate. And maybe consumer electronics, automotive, healthcare, it will be somewhere out there. But we need to find those killer apps. I think we know how to justify the bespoke processor today, but for general purpose, we need to find those applications where the software update or change required for those applications. Like today, the way we do the IoT devices, we do firmware updates regularly. So if you need to do this for flexible device, then you need to make it programmable, meaning it has to be general purpose. All right, so now, so bespoke processor is a very generic concept. So under the bespoke umbrella, bespoke machine learning processors, which is what the topic of the talk. So this is our envision for the future flexible integrated smart system. So you have everything flexible, everything made of flexible components. There is no hybrid integration in this vision. So flexible sensors, interface, ADC, and whatever you have there, and then flexible machine learning processor. They just get the sensor data and it does something, maybe classification or making some decision about the sensor input it receives. It could be homogeneous sensor or it could be heterogeneous sensor, it doesn't matter. And then there will be some set of I/O devices like NFC and display, and then eventually they will be powered by the printed battery. So this is our vision, but there will be definitely a local compute happening. So the compute will not be ignored. It has to be done locally, at least a portion of it locally. So this is our current project called PlasticArm. So we claim that this is the first flexible bespoke machine learning processor, and it's an additive. If you remember the additive subtractive classification, so this is an additive bespoke processing for ambient intelligence. So what we are trying to do is we're trying to build this processor coupling with the flexible e-nose sensor, electronic nose sensors, and what it does is when you put the entire system your underarm, it scores how bad your underarm smells. Obviously, this is coming from a real application, so Unilever is a partner in the project, so they describe the application. And there is an actual use case for this. I can't go into details, but what I can say that this is a very, very key application for deodorant industry in Unilever. So the project started in 2017, it's still ongoing. So what we are building is something like this. There are three main components in the project. The other components we are getting, we are not working on the project to develop. So what we are developing is the eNOS sensor, custom eNOS sensor, all flexible. An interface, reading the sensor information and converting into digital world, and then a custom classifier, and then some kind of display, which will be acquired outside of the project. And eventually it will be something like this. So there will be a sensor array on the left, smelling gas, and ADC, some level of ADC, and then some flexible machine learning bespoke processor. It shows a neural network type thing, but it's more generic. And eventually we will have a strip like this, integrating all these components, very tiny strip. It goes to your underarm and then it scores you. That's the vision. Okay, so ARM, Pragmatic, and Manchester University, so we build this framework. So what it does is at a very high level, let's not confuse you with the details. So at a very high level, what you give us is the sensor data and the application requirements. We fabricate the chip, and the wafer, flexible processor wafer, custom for your application comes out using this tool set. It's not fully automatic, but it's kind of semi-automatic. What it does is that you take the application and the sensor data. We have some libraries of machine learning software models, training and inference. So we use this data, and then we build a software model. From the software model, the hardware model is generated. So we are using all Python here, so there is no hardware description language yet. And then once we find the best model, best hardware model, and this is validated, so this runs, essentially it's a simulation. Take the software model, hardware model, runs. If there's a match, then the Verilog is automatically generated for this processor, and it goes to the front end, simulated again, Verilog simulated again, and it compared to software and the high-level hardware model, and the requirements check is done. If the gate count, your power, performance numbers match, then you start to backend and implement it, and you tape it out and fabricate it. If not, then it is iterative. It goes back to hardware library as well as software library. Several iterations. Once this is optimized, what you get is application to fabrication with 2 to 4 weeks. You give the data and the application. You get your bespoke processor on a flexible substrate within 4 weeks. So I like to, this is my last slide, I believe. The business and research opportunities. I think there is still need to build this flexible, integrated, smart system. Lots of I see in a lot of presentations about sensors and and maybe battery harvesters, etc. But the full system is what is important. So I noticed that the processor side is always neglected because there is no solution that we can use silicon, MCUs and blah blah. But there is now more opportunity to adapt this framework. This framework is not just for eNOS, so it can be used with other type of sensors. For example, we added like tactile image and pressure, blah blah. And what is two things are missing at the moment: a good system integration. How do you integrate all these systems cheaply at a low cost, and a good processing development framework. So again, we are open to discuss with other partners. I think ecosystem formation is key here. If we form this like the way we do in the silicon world, especially ARM does this very well. Lots of different partners get together, and then we'll find the killer apps, as they said it in the marketing terminology. So key takeaways. We believe that there's two things happening now: lots of high volumes and short lifetime, product lifetime, as well as low cost and flexible fabrication allow for the first time bespoke processing for the specific problem. And then now we have this tool set. We can actually create, you don't have to spend years. You just use this tool set to create your bespoke processing environment and it will reduce the time to market. And we are open to discuss forming this ecosystem on around flexible electronics. Thank you.